We are returning once again to our three single-phase transformers, each with a rating of 5 kVA and a turns ratio of 200 to 100 at a frequency of 50 Hertz. If the high side is connected in delta and the low voltage side is also connected in delta configuration, our task is to find what line-to-line three-phase voltage should be applied in order to maintain the rated winding voltages. Also, we are to calculate and show the line and phase current magnitudes in both the low voltage and high voltage sides, corresponding to the rated conditions. Finally, we have to calculate the kVA flowing into the primary and out of the secondary of the transformer at the rated applied voltages. These are still the three identical single-phase transformers, but connected in delta-delta. The rated current of each high-voltage coil is equal to the kVA divided by the high voltage across the winding, which is 5,000 divided by 200, which is equal to 25 amps. Using the same logic, the rated current of each low voltage coil is 5,000 divided by 100, or 50 amps. The line-to-line voltages to be applied to the high voltage side is easy because the windings on the primary side are connected delta to delta, which means the line-to-line voltage is the same as the rated winding voltage, 200 volts. And the line-to-line voltage to be applied to the low voltage side for the same reason is 100 volts. Since the coil current has to be at rated value, the line current on the low voltage side is equal to the square root of 3 times 50, which equals 86.6 amps. And the line current on the high voltage side is equal to the square root of 3 times 25, which is equal to 43.3 amps. The total kVA output is root 3 times the line-to-line voltage times the line current on the low side, which is equal to the square root of 3 times 100 times 86.6, which is equal to 15 kVA. And the total kVA input is root 3 times the line-to-line voltage times the line current on the primary side, and that is equal to the square root of 3 times 200 times 43.3, which is also equal to 15 kVA. Again, the power going into an ideal transformer must equal the power coming out of an ideal transformer. And we also see that the kVA total for three transformers is 3 times the individual kVA rating of the transformers. In recent years, the reality of climate change has become impossible to ignore. Severe weather events are growing more frequent and more intense. For homeowners, this means that utility power outages are no longer inconveniences. They can last for hours, days, or in extreme cases, even longer. The question is no longer if, but when. You'll need a solution to keep your homes powered and your family safe. Now is the time to prepare and ensure that you're not left in the dark when the next storm hits. Here are some trusted resources to help you prevent power outages at home. 𝐃𝐈𝐒𝐂𝐋𝐀 Canada at this web address, 𝐃𝐈𝐒 USA at this web address, Bluetti Canada at this web address, Bluetti USA at this web address, and Bluetti Australia at this web address. And finally, you can get EcoFlow at this web address. Ready to go beyond just solving problems? If you've been following my daily post and enjoying the sample problems, you're going to love this. All of these problem sets and more are now available, or soon will be, on my official course site. My stands for electrical training. Just go to the web address that you see at the bottom of this slide, https://stand.store/GVB.